Hello everyone, welcome to the Innovation Lab. In this video guys, we're going to build this high power, constant current and constant voltage DC to DC boost converter from scratch. And all you guys are going to need are some design components that's going to go on the board. And you're going to need a Veroboard and soldering iron. And that's pretty much it guys. If you can follow a schematic, which I'm going to provide in this video, and you can solder, I believe you should be good to go. All right, my friends, let's get started. Alright guys, so I started this YouTube channel as my small way of inspiring other people, as my small way of giving back to the DIY community. So I'm making this video to show appreciation to all of you for inspiring me and also supporting the Innovation Lab. So in this video, we're going to go over the design schematic. I am also going to be able to provide the free PDF version of the schematic to you guys, but I want you guys to also watch the video first, because a lot of times what I get is a lot of people will just look at the thumbnail of the video and they'll just go straight to the comment section and ask for schematic. The thing with that is, without watching the video, you're gonna have a lot of questions and you're gonna come back to me with all those questions, and I don't want to spend too much time explaining something that I've already explained in the video. So to ensure that you guys are going to watch the video, so what I'm going to do is to provide you guys a code at some point in this video, and all you have to do is to reach out to us at the Innovation Lab with that code, and we'll provide you with the PDF version of the schematic. This was originally intended to be a fun DIY investigative research project, which I was using to fully unpack the functions of the TL494 PWM circuit. I didn't intend to make this a video, but as I go along, I learned a lot of things. I thought this would be a good idea to share this project with you guys. Alright, so in this video, we're just going to focus on building the converter. We're going to apply some load on it, and we're going to look at the efficiency or performance of the converter as we apply different loads, and also drive the converter with different input voltage levels. And towards the end, I'm going to take my time to go over the design schematic with you guys, pretty much almost line by line, to explain everything that we have on this design. Also, I want you guys to know that I still have a lot of tests that I want to conduct on this converter, and those tests I am hoping to capture in the next video. Alright guys, one last thing I would like to mention here is that this is a DIY project and I'm sharing it with you guys. What you guys choose to do with it is all up to you. I'm not going to tell you guys what to do. I will highly encourage you guys to make sure that if you're going to interface this design with any equipment, make sure that that equipment is not sensitive to ripples, and if they are, you have to be able to find a way to test your converter to make sure that input ripple, output ripple that you're generating is within the limits of what those electronics around it can handle. So having said that, please don't go building a DIY converter and plugging it into your expensive BMW. That would not be a wise thing to do. That is something I would not do myself. If you guys look on my test setup, you see that I am driving all of this using my DIY server power supplies. Those are cheap server power supplies that if they get damaged, I can easily replace them, or I'm driving them or using them to charge my battery system. So everything you see on my setup is dedicated to testing. So if any of those goes bad, I can easily replace them. Alright guys, so that's the premise of the video in a nutshell. So let's jump right into the build. Alright, our build is complete. And I'm going to be using my 24 volt power supply here that is made up of series parallel server power supplies to test the DC to DC boost converter. So one of the things I like to do whenever I'm conducting the initial power up of a fresh design like this, or maybe when I am powering up a converter after repairing it, is to add an inline 4 ohm resistor or maybe a slightly higher resistance value if you have that in series with the power supply positive that is coming into the converter. So doing that serves two purposes. So the first purpose is to mitigate the high inrush current that's going to hit the input caps of the converter. So the second purpose is to provide a low current startup to make sure that the PWM circuits, the MOSFETs, the power inductor, everything is going to perform as we expect, because if you have a short or if you have a problem somewhere, you don't want to bring in all the power at once. So doing that allows me to just connect the DMM at the output of the converter with no load, enable the PWM, and kind of vary the output voltage. So that tells me that the actual converter circuit is working as expected. Alright, so now that we know that the converter actually works, so the next thing I have to do is to bypass that series resistor at the input of the converter and apply a small load, preferably a resistive load. And after doing that, I slowly increase the output voltage that is going to that load. And doing that allows me to see the maximum output voltage possible that the converter can attain based on the design. So with the load applied, as you guys can see here, and an input voltage of 24 volts coming in from the server power supplies, I was able to slowly increase the output until I got to about 100 volts. I believe that was the maximum for this design. If I want to go higher than 100 volts, there are things I have to go tweak, components and settings to be able to get to higher output voltage. And also, as you guys can see here, we were able to apply a load of 238 watts at the output of the converter using the light bulb. And looking at the input versus the output power, what we can see here is that at this stage, this converter system is performing at 85% efficiency. Also at this stage, I was curious to look at the peak-to-peak ripple voltage that's going in and out of the converter. So what I'm seeing here, given these test conditions, is a peak-to-peak output ripple of 1.6 volts. Given that we're driving this to 100 volts, so that puts the output ripple percentage right around 1.6%. And then also we measure the input ripple and we're seeing 1.2 volts peak-to-peak. And again, given that our input is right at 24 volts, so that puts us at around 5% ripple. And lastly, given that I added the PWM enable switch on the converter, so I wanted to see how effective the PWM enable switch is going to be in terms of controlling the output power that is going out of the converter. And as you guys can see here, it's doing it quite efficiently. So the next test I conducted was to apply a heavier load on the converter, and my goal was to see if this converter could deliver up to 1000 watts of load given an input voltage level of 24 volts and stepping that voltage level to about 70 volts to my load. So this is the same exact test configuration. So the only two major things that changed here is the actual load that I'm going to apply at the output of the converter. And also I wanted to see if I can improve the ripple response of the converter by redesigning the power inductor to an inductance of 57 microhenries instead of the initial 21 microhenries that I used previously. And as we go through this video, you guys are going to see different iterations of those designs show up on the test setup. So as I was going through the testing, so I had to make a lot of tweaks, and you guys get to see it as we progress in this video. So having said that, the next thing I had to do was to really connect the load and slowly increase the output voltage of the converter until we got to about 70 volts, as you guys can see here. And one very crucial note for you guys is to make sure that you add a strong cooling fan to the setup. I wouldn't just rely on the heatsink by itself. You also need a fan to help the heatsink maintain the thermal stability of the system. Alright, so when we get to 70 volts, we had to take a pause to kind of look at the performance of the system under these conditions, given that we're using the converter to drive a 24 volt to 70 volt. So looking at our current probes and DMMs, what I'm seeing here is that we're delivering about 15 amps to our load at 70 volts. So that gives us an output power of 1050 watts, which is 1050 watts, and an input power of 1132, and that means an input voltage of 24 volts and a delivered input current of 47.2 amps that is going into the converter. So when we do the math, that gives us a converter efficiency of 92%. For the 36 volt testing, we repeated the same exact steps, the same exact test setup. The only major thing that changed was the power source. Instead of driving the load with our 24 volt server power supply, now we're using our 36 volt lithium iron phosphate battery system that is made by LiTime. This is an amazing product. It has been part of my test setup for a long time and it delivers good efficiency. It holds charge. I am really happy. So LiTime sent me this unit a while ago for me to review, and since then it has been part of my test setup. This video is not sponsored. I am just saying this to give a shout out to LiTime for making really good products. And if you guys would like to see the review video that I've made on this product, I will leave a link in the description of this video. You guys can go to my channel and check out the video. Alright, so given that now we are driving the system with a slightly higher input voltage, so I wanted to push that output voltage a little bit higher. So the benefit of using a slightly higher input voltage source is that you should be able to push out more power at the output of the converter without stressing the input power section of the converter too much with high currents. So because of that, I was able to push the output voltage level of the converter to about 85 volts. And looking at our measurement, we are measuring an overall delivered output power of about 1507 watts going to our load with an output current of 17.7 amps going to that load. And looking at our input, we were able to pull in about 1623 watts as an input current going into the converter of about 43.2 amps. This is quite impressive. So one thing to mention here is that given that we are now driving this converter with a battery system, so one thing you guys know about battery systems is that over time the voltage will keep dropping, so it's not going to stay consistent. So but one of the big characteristics of a DC to DC converter is to be able to maintain a constant output voltage level even though your input voltage is dropping. So I just wanted to mention that. So again, with output voltage set to 85 volts, I took a quick pause to look at efficiency. So looking at our input and output measurements, what we're seeing here is a calculated efficiency of 92.8%, which is quite impressive. Alright, so once I saw that efficiency number, I was really curious because I knew that with a 36 volt input, I should be able to push even more power out of the converter unit. And that really encouraged me to see if I can push the system a little bit more. So in a nutshell, I was able to increase the output voltage to about 90 volts, as you guys can see here. So we're delivering about 19 amps at 90 volts to the load with an input current of 49.8 amps. So overall, we're seeing about 1700 watts delivered to our load. We're seeing about 1857 watts coming into the converter, and when we do the math again, we're seeing a converter efficiency of 92%. Again, we're only losing about 8% to heat and all the losses that is going on in the converter. So in my opinion, if you ask me, I'll say that's quite impressive. Alright, so in this segment of the video, we're going to talk about the design schematic. And before we go into that, let's go ahead and take a quick look at the PWM chip, which we will consider in this case as the brain of the design. I found two very good data sheets. One is from onsemi and the other one is from Texas Instruments. Both of them are quite good. I like to use the onsemi one when I'm making reference to all the pin configurations, as you guys can see here. So this one shows us a more labeled configuration of all the pins of the TL494. So here you can see the two error amplifiers connected to pins 1, 2, 15 and 16. The first error amplifier is used to implement the voltage feedback control, And the second error amplifier is used to implement the current feedback control of the PWM chip. And going down, you see pin 3 is the compensation pin. Pin 4 here is the dead time control, which is also very important because actually in this design, pin 4 is serving about 3 functions. One is to implement the soft start function of the circuit. The second is to serve as a PWM enable switch because I can turn off the PWM using pin 4. And the last one is really the dead time control of basically this pin. How much voltage you apply to this pin will determine the length of time that these internal transistors Q1 and Q2 that is driving the output will stay off. So all of that gets factored into the design. So CT pin 5 and RT pin 6 are the oscillator pins. So that means that we're going to connect our oscillator capacitor to pin 5 and oscillator resistor to pin 6. And these two values are what we're going to plug into the switching frequency formula of the oscillator that drives the PWM chip. Pin 7 is the ground. Then we have other pins like pin 8, 9, 10, and 11 that connects to the internal transistor, the open collectors and emitters. Pin 12 is VCC. Pin 14 is the reference 5 volts that's going to come out of this that we will actually use to set other reference voltages for the error amplifiers. So I wanted to take a quick pause to explain this chip for you guys pin per pin. So when we make reference to each pin on the schematic section, so you guys can easily associate those references to the pin configuration of the PWM chip. Alright, so I took my time to capture the schematic to make sure that all the changes, every component I have on the board is well documented. And for my schematic capturing, I use a software known as Deep Trace. So Deep Trace is quite good and there is a free version of it that you guys can download. And if you're looking to do more things, you can get the paid version. So it allows you to do schematic capturing. They have models and symbols of all the parts, resistors, ICs, capacitors, you name it, is all in there. And it also allows you to take that schematic that you've captured and export it into a PCB layout and you start laying it out, which is quite good. So feel free guys to go check out the Deep Trace design tool. I highly recommend it. I've been using it for many years now. Alright guys, I'll do my best to go over this schematic as quickly as I can. So I broke it down into 3 pages so that way we keep it nice and neat. So the first page here is the input power and auxiliary power stage of the design, and the second page here is the input overload protection circuit. The last page is actually the moneymaker, which is the PWM control and MOSFET driver and everything else circuit. So going back to the input, so as you guys can see here, so this here covers the input positive connector, the fuses, and the input capacitor bank. So one thing I recommend is that the input capacitors, you want to place them as close to the power inductor as you can. So the advantage of placing these input caps as close to the power inductor as possible is to help us dissipate or knock down or minimize, depending on how you look at it, the input ripples that is going to be caused by that inductor switching on and off and on and off at a very high frequency. So that means that if you don't take care of those ripples, they're going to find a way to feedback to your power supply, and you don't want that. All right. So, and on the lower side of things, we have the input power negative or the return connector. And from there, we have these input current sense shunts. So in this design, I added the input over current protection circuit. So what that does is essentially to read the voltage drop across these 2 nodes here and here, which is set by the network of shunts that we are using here. And I'm going to talk about it on page 2 when we get to that point. And here is the auxiliary power section of the design. So essentially this is the power that's going to be driving everything else on the board. It's going to be driving the PWM controller. It's going to be driving the MOSFET driver and everything else. And I had wanted to use an off-the-shelf DC to DC buck converter, as you guys may have seen in the build section of the video. The reason I changed it was that converter was highly limited because it can only go up to 36 6 volts, and I wanted this design to have an input voltage range that goes up to 60 volts. So the way this works is quite simple. The power comes in from here, and I'm using the blocking diode here to make sure that we don't feed back power to the input. As you guys can see, the highlighted net here, it goes through these 2 Schottky diodes, and I have my LC filter here, the first stage that filters the power that goes this way to the regulator, and I'm using a Zener diode configuration to set a 12 volts going voltage here, and I'm using that voltage to drive this N-channel MOSFET in the source follower configuration. And then I have a second stage of my LC filters here before we now send power to our load. The idea is that whatever comes out of here is gonna be highly filtered, and whatever high pulse switching that is going on in the power section of the converter is not going to affect this too much. The function of this Zener diode is to basically protect our components when we have a kind of failure of this N-channel MOSFET here. So when there is a failure of the N-channel, all the voltage wants to shoot through, but this Zener will block it, and the Zener blocking it will cause this fuse to blow, which is exactly what we want. All right, that's page 1 in a nutshell. So page 2 is the input over current or overload protection. So this is essentially a voltage comparator configuration, and I'm using LM358. So we're sensing the voltage drop that is set by our load through here, and it goes to one of the voltage comparator modules of the LM358 pin 5. There are 2 of these inside the LM358 module that I'm using. I'm only going to use this one, and the other one will remain unused. So how this works is that we're using this voltage divider network here to set a specific voltage that corresponds to the maximum amount of current, which when exceeded, the converter will trip. So for example, let's assume that you want your overcurrent threshold to be exactly 100 amps. Now when we go back to the input stage of the converter, so you see here that I'm using a network of 420 milliohm shunts. So that gives us a resultant shunt of 5 milliohms. So what that tells us is that when we have a current of 100 amps that's trying to flow through this shunt network, we are going to set a voltage drop of 500 millivolts across the shunts here, which is between this node and this node. There's going to be 500 millivolt drop, here being the ground and here being the positive side of that voltage drop. And as you guys can see, so now we go through this 1 ohm resistor here and send this information through this node here to page 2, which is our OCP circuit. And our voltage comparator is always listening and comparing what's going on here with what's going on here. This node here will have a reference voltage of 500 millivolts, and this node here is waiting to get to 500 millivolts to give us a high output. So if here is at 500 millivolts and whatever current you're driving is setting this node here to 300 millivolts, the output will not trip. It sets it to 400 millivolts, the output will not trip until you actually get to 500 millivolts. Then you have the output here will go high. And so what I'm doing here is to use an SCR. When the output goes high, this SCR will turn on kind of a one-shot operation. Once it turns on, it can never turn off again, and that's exactly what we want. Because it now goes high, we have this LED that's going to come on to tell us that we have an overcurrent trip. Then we have this second MOSFET here that is in the source follower configuration that is going to turn on, allowing the positive voltage to flow through here to go to the shutdown pin 4 of the TL494. And that will bring us to the last page of the design, which is the TL494 PWM control and the MOSFET driver circuit. All right, so there is a lot in here. So guys, if you have a specific question, you can try to leave me a comment, or you can join my Patreon Q&A membership. So it's only $5 a month, and I set that up to be able to help me explain things like this to you guys, because there is a whole lot to unpack here. So going over from left to right, we have the boost enable switch tied to pin 4, the dead time control. We talked about it in the beginning. And also what you guys see here is when I talked about the soft start circuit is right here, which comprises of these 2 components here connected to 5-volt reference and 1K to the return. That gives you that soft start function. So what happens is that when you don't have this soft start circuit here, when you go ahead and you turn on this switch, so your PWM output is going to jump to about 96%. That may not be good. So that could, break your MOSFET or do something that you don't like. Yeah, so that's very important. And as we talked about earlier, pins 1 and 2 here connect to the first air amplifier that controls the voltage feedback of the chip. Pins 15 and 16 are tied to the second air amplifier that controls the current feedback operation of the TL494 chip. So here we have the output current reference voltage that allows us to set the output current limit, and that is tied to the inverting pin of the second air amplifier inside the TL494 chip. So what this does here is that when you set a reference voltage, so that voltage is what the second pin, pin 16, is going to use to compare. Again, if you guys remember when we talked about the function of the input current sense shunt, how it sets a voltage with respect to how much current is going through it. So that is the same thing that this shunt does as well, but it does it on the output side of the board. So if what is coming in here is lower than the reference that is set here, it tells the chip to increase the on state of the duty cycle that is driving the MOSFET. And when both of these voltages, what is measuring across the shunt versus what is measuring at the reference voltage setting, equalizes. So what happens now is that the chip is smart enough to now tell the system, the oscillators, it now gives the PWM control back to the air amplifier that is controlling the output voltage. So you have kind of a harmony between the voltage feedback and the current feedback. So the overall control goes between the voltage feedback loop, the current feedback loop. It goes between the voltage feedback air amplifier and the current feedback air amplifier. So they kind of work hand in hand. Also, if you look at earlier when I showed the internal configuration, so you guys will see that the outputs of both air amplifiers are connected together and goes back to pin 3, which is called a compensation pin. This 33K sends a little bit of a feedback to pin 2 to be able to help stabilize the system. And the information I found from the TI datasheet was that your goal should really be to make this compensation resistor as close to your RT, which is the oscillator resistor, as possible in value. So as you guys can see here, I'm using 33K here and 33K here. Or you can use slightly less value here depending on what frequency you want, and that will also work. Yeah, so from there we have our output. So this is the PWM output that is coming out of the TL494, and that goes to the input of the MOSFET driver circuit here. Pin number 2 comes out of pins 7 and 8. This Zener diode here serves two purposes. The first purpose is to clamp off unwanted transient voltage spikes that could damage the gate of this MOSFET. The second purpose is actually to protect the MOSFET driver. So if you have a situation where this MOSFET fails, so you can possibly have a flatback current or voltage that is high enough to feed back all the way and damage this MOSFET driver. And I have seen this happen too many times. So adding this Zener here helps protect that. So here is our power inductor for this design. So for this design, I've tuned this value within the ranges of 21 to about 57 microhenries. I changed this to 57 microhenries. I really wanted to see if I could lower the inductor ripple current that is coming out of this system, because that could also lead to high output ripples, especially if the caps that you're using here are not super low value ESR caps. So the MOSFET I'm using here is the HY3912. There's a bunch of other ones that you can use, but I am using the HY3912, or you can also use the HY5012. I believe in the past I've also used IRFP110 and it does work quite well. So what you want here is a MOSFET that will give you a very low RDS on value. So RDS on is the drain to source resistance when this MOSFET has been turned on. So basically when we turn on this MOSFET, it begins to act as a switch. So that will be this resistance going across that switch, and you want a MOSFET that will give you that value in single digits milliohms. The other components to look at here, the output stage will be the fast recovery diodes. So you want to make sure that you find, first of all, a diode or rectifier that is considered to be a fast recovery diode. The key parameters to look for here will be the reverse voltage rating of that diode. It has to be higher than the maximum output voltage you're hoping to get to with this boost converter, and the forward voltage rating of the fast recovery diode, because that translates to how much voltage drop you're going to see going across each of these diodes. And if you have a lot of voltage drop, that means you're going to be dissipating a lot of power on these diodes, and that is going to affect the overall efficiency of your DC to DC boost converter. And the last thing to consider, which is also one of the most important for this diode network, is the forward current of each of the diodes. So for example, if you're designing this to be able to provide 50 amps, you might want to choose a diode network that can actually allow 50 amps to go through it. So if 50 amps is my design output current max, I will select these diodes such that each of these will be rated for at least the forward current of at least, I want to say, about 40 amps each. So this network should be able to support about 80 amps. So now you derate it down to 50 amps, they will perform better. And lastly, here we have our output capacitor bank. So the only thing to keep in mind here is to make sure that the voltage rating of the caps that you select is higher than your maximum output voltage that you're going to drive this guy to. So if you're building a 300 volt DC to DC boost converter, for example, I would actually change these caps here to a voltage level that is way above 300 volts. The second thing to consider is that you want to make sure that you use very low equivalent series resistant capacitors. A good capacitor should have an ESR value that is in milliohms. The lower, the better. And the reason for this is that low ESR value capacitors will always result in lower peak-to-peak output voltage ripple or output current ripple that's going to come out of your converter. And the reason why, as you guys can see here, I use multiple caps in parallel, this is quite a good practice, is if you use just one cap, you're not going to be able to lower that ESR, just like resistance is connected in parallel. So connecting these caps in parallel makes the ESR value, not the capacitance value, the ESR value, to be as low as possible. So we have to be mindful of that. Yeah, so this is it in a nutshell, guys. I am going over a ton of information that has taken me months and years of experience and research. I'm packing it into a few minutes of video. And if you guys have any questions, feel free to reach out to me. And if you want a more detailed explanation of some of these stages, feel free to sign up for my Patreon Q&A membership. It's only $5 a month. All the money that's going to come out of that goes back into building on this project. It funds the videos that we make. It funds our website. And so that way you guys get to support the work that we're doing. All right, guys. So that is the design schematic in a nutshell. Alright guys, so what we just went over is the design schematic, but I do have other tools like the one we're looking at here that allows me to calculate the fundamental parameters that I consider when building a DC to DC converter. All I have to do is to plug in the boundary conditions per se of the design, and this tool here will kind of give me all those parameters that I always consider, things like the inductor ripple current, the actual required inductance of the power inductor, and we have to consider the max switch current that is required to give me the maximum power that I need, and we look at the duty cycle and all of that. Also, having a working schematic when building a converter system is not necessarily gonna guarantee you good performance. You also need to know some PCB layout tricks, or if you're gonna build this on a Veroboard like I just did, there are some rules, some do's and don'ts that you don't do if you want to have an efficient converter system. I'm not going to be able to pack in all of that information in this video. If not, this video is going to last for 4 hours. So one help that I need from you guys to let me know if this is a subject that you guys would want me to cover in the future video is to leave me a comment that says design tool and layout. So by the time I get 100 comments that says design tool and layout, I promise you guys that I will start working on that video. And the reason I say that is that making these videos takes a lot of time and a lot of effort. So if I'm going to invest all that time, I want to make sure that I'm using it to bring you guys good value. Alright guys, I promised earlier, I'm going to be sharing the PDF version of the design schematic with you guys. All you have to do is to reach out to me through my website at theinnovationlab.com and include a message that says DIY boost converter design schematic, and that's it. And when I see that, that tells me that you actually watched the video, and I will send you the PDF schematic. Alright guys, so one of the things I wanted to fold into this video is to show you guys the application or the use case of a project like this, which is in this case we're going to use it as a battery charging system. So we have our 24 volts coming in from our server power supply, but we have this battery system here. This is a 36 volt nominal battery system. The actual required charging voltage for this battery is right around 44 volts. So without this DC to DC boost converter system, we're never going to be able to recharge this battery unless we can actually afford to buy the charger. Essentially, what we're going to do here is to use this DC to DC boost converter to boost the 24 volts coming in from our server power supplies to about 44 volts that we're going to use to charge this battery system. I'm sure that most of you guys with very keen eyes would have seen that the inductor that I'm using for the battery charging test is different. I conducted this test back when I had the 2-in-1 microhenry inductor installed, and I'm going to be able to talk about why I changed it to the 57 microhenry is actually because of this battery charging test, as we talk about the ripple voltages later. So to be able to use this converter as a battery charger, I had to do a few steps. So the very first step I did was to increase the output current limit of the converter. And after that, knowing that the required charging voltage of the battery system is about 43.5 volts to 44 volts. So all I had to do was to set the output voltage of the converter as close to 40 volts as possible. And the reason I did that was to allow me to use the output voltage adjustment potentiometer kind of to control the amount of current that I'm going to deliver to the battery system. And having done that, the next thing to do is now to connect the battery system at the output of the converter, then enable the PWM, then slowly now increase the charging voltage that is going to the battery system. And as you do that, you keep an eye on the current clamp. So in a nutshell, all I had to do was to slowly increase the output voltage of the converter, which is now the charging voltage of the battery system, until the delivered charging current that is going to the battery gets to about 25 amps. Alright, so given that we're using this as a charging system, so I was really curious to look at how clean the delivered output power going to the battery system is. So what I'm seeing here is a measured output peak-to-peak ripple voltage of 6 volts and the measured input peak-to-peak ripple of 2 volts. So to be fully honest with you guys, a peak-to-peak ripple of 6 volts at about 40 volts of output voltage going to the battery system is quite high, and that was what drove my decision to redesign the power inductor going from 21 microhenries to 57 microhenries. And my plan was to redo the battery charging test to see if I get a lower output ripple going to the battery system. And unfortunately, before I could get to that point, my curiosity led me to blow in the MOSFETs because I put more load on the system. And that notwithstanding, I plan to conduct more testing in the future to really look at the input ripples at the different loads, output ripples at the different loads, and see what I can do to actually mitigate that, being tuning the inductor for better performance, or possibly looking at the equivalent series resistance ESR of the output caps that we're using on this converter. So in a nutshell, guys, all I'm trying to tell you guys here is to stay tuned. If you are not a subscriber, make sure you subscribe to the Innovation Lab. So in the future, when we conduct all those tests, you will get notified as we release all those videos. Alright guys, we have come to the end of the video. Thank you guys for watching. Thank you guys for always supporting our channel. As you guys have seen in this video, building a DIY converter from scratch is quite feasible. And as you guys have seen, we have been able to build a converter system that can deliver close to 2000 watts of output power. But there are other things I would like to go over with you guys about the design that we're not going to be able to fold into this video. If you guys would like to see all of that, go ahead and let me know. Leave me a comment. This project is all for you guys out there that like to build things, and it's my way of appreciating you guys for always supporting the Innovation Lab. Alright my friends, I hope you enjoyed the video. I hope you learned something from it, and if you did, don't forget to give the video a like. And also, if you're not already a subscriber, consider subscribing to the Innovation Lab. You can also inspire all the work we're doing by becoming a Patreon supporter. Alright my friends, I'll see you guys in the next video.